Oh, well, I'll have to do that later. That was really awesome. I'm going to redo the tissue, the Kleenex fountain at the end of class. Okay. So I'll do it again. I'll do all the shielding again, and it will be amazing. All right. So let's review the case where if we have, say, a conductor. All right. So we have a charged metal sheet. Hey, we put some positive charge on here. Of course, the positive charge is going to go to the outside of my metal conductor. Okay, it moves to the edges. The charge always lives on the surface. Okay, so it will spread out to the surface. Now I'm going to draw a Gaussian cylinder here, like this. Okay. And there's my Gaussian cylinder. And so in this case, I want to find what the electric field is here, let's say at the end on the surface of my Gaussian cylinder here, okay? Well, inside here, there's no electric fields, okay? Because inside the conductor, the electric field is always 0. Outside, I know that the electric field is always perpendicular to the surface, okay? So that means the electric field is not going to penetrate the sides of my cylinder here. It's only going to come out of the end. So the electric field is only going to go through the end here. Okay, so let's do the math now. So for my Gaussian surface, okay, well, I've got my electric field dot dA, and remember that dA is a vector that is perpendicular to my surface. So whatever my surface is here, so it's pointing away from the metal sheet, is perpendicular to that flat end on my cylinder, and it's in the same direction as the electric field, okay? So when I do my integral here, E is constant everywhere over the surface, so I'm just gonna get E times the area of my surface, okay? And I know that this I can always write is equal to Q over epsilon naught, okay? But now we have a surface charge density, and so we're going to replace Q. We're going to say Q is equal to sigma dot dA, okay? And this is just equal to sigma times A, which is equal to Q. And so the surface charge density then is equal to Q times Q divided by the area. Just want to review that just for a second, okay? So now I can plug this in up here for Q, and I can say the electric field times the area is equal to my surface charge density times the area divided by epsilon naught. My area is going to cancel, and so I just end up with epsilon times sigma times epsilon naught. Okay, now, so that means if my sheet here is infinite, okay, and I am some distance away, then it's not going to matter how far away I am from that surface. Okay, now, of course, if you're really far, then this starts to break down a little bit. But if you're close enough here, and if you're in a region of uniform electric field, then this is true. Okay, so, and for our class, you would use this equation right here. So you would say, all right, how much charge is on my surface here? What's my total surface area? So what's my Q total here? Okay, and then divide that by the area of one of my sheets. So presumably you have a squared sheet like this, okay? So that's your total surface area. So area is equal to length times width. That's your area. And then you need to know what your total charge is on there, and that is sigma, okay? So I think that part should hopefully be review, right? So let's move on here to something else. I want to do a little conceptual problem here, and I hope that you know the answer to this one. Maybe you do, maybe you don't. I hope that you do. All right. So let me put this up on the screen here. All right. So take a look at this. A cylindrical piece of insulating material. So this, imagine we actually have a cylindrical chunk of plastic. All right. It is closed on both ends. Okay. And we put it into an electric field. Okay. And our electric field looks like this. Okay. So you see these field lines going out. They penetrate the cylinder. Okay. And it's imagine you have a big cylinder of plastic. Okay. So you have a big like soda can shaped piece of plastic. All right. So what is the net flux, the net electric flux through the surface of the cylinder? Okay. So we put it in an electric field, right? And it's plastic. So remember the plastic ball, right? Doesn't work as a shield. Okay, so electric field goes through it. All right, so what is, oh, and yes, please put it in the chat privately to me. Let's take a vote. So is my net flux going to be A, positive, B, negative, or C, is the net flux going to be 0? Put your answers in the chat and let's see what we get. Okay, so got a few answers coming in. I see there's about 35 of every people in the class. I hope to get at least 35 or maybe 34 answers. Okay. All right. So we've got a lot of answers. It looks pretty split. I'm seeing looks like mostly A's. Okay, mostly A's. I see a few B's and a few more C's. Okay, well, I'm gonna, let's see. So yeah, looks like everybody's pretty much answered. So I'm gonna put you in breakout rooms just for a minute or two. I want you to talk about this with your neighbors and think about how much charge is enclosed in this piece of plastic based on the electric field. All right, I'm going to put you in breakout rooms real quick. Talk about it with your group, please, and then we'll come back and we'll have another vote, and I'll see if it gets better or worse. So, all right, go to breakout room just for a minute. Talk about it. C, there, oh, yes, okay. So think about, is there charge in that cylinder? Go to your breakout rooms, please. If you haven't done so, please go to your breakout rooms. Discuss it with your partner, and then we'll bring you back.
I think so. It looked like it was to me.
Hey guys,
Yes.
what do you think?
We say positive.
Okay.
Yep.
And is there any charge inside of the plastic thing?
No, I don't think so.
Okay. So then what is the total flux then if there's no charge inside?
Oh, so would that be 0 then?
Yes, because I lost my pen. Okay, yeah, because you guys remember that flux is equal to Q enclosed divided by epsilon naught. So if I have no Q in there, right? Because you were correct to assume that there is no actual charge in there based on how the electric field looks like, then That means the flux is 0. Okay, I'm gonna go back.
That makes sense.
Thanks, guys. All right, so let's take another vote when you come back. Let me put it back on the screen. All right, so please vote again if you can. Put it back there. So is it going to be A, positive, B, negative, or C, 0? Look at my paper. All right, so let's see what's coming in on the chat. What do we have? So on the chat, oh, it looks like we're getting a lot of A's and a lot of C's. Let's see. Okay, well, all right. So somebody that answered C, why do you think it's 0? Somebody please tell me. I think you guys can talk in the chat. You're not muted. Somebody tell me why at the answer you think it's C. A brave soul, because everybody's really nice here. Who wants to say it? Because the amount of electric flux entering the cylinder is equal to the amount of flux leaving the cylinder. That's right, because all of the flux that goes in one side comes out the other side, okay? Now, I can tell from my drawing here, if I look at these electric field lines, okay, they don't appear to be originating from any particular source that could be inside of the cylinder, okay? Because if I had a charge, say, inside of the cylinder, if it were positive, it would look something like this, right? I'd have field lines coming out of my cylinder, or if I had, say, I'll erase those ones. If I had, say, a negative charge, then I'd have a bunch of flux lines going into my cylinder. They'd all be centered at, say, a single point here, okay? That's if I had a negative charge, right? They'd all be focused there. But based on this picture, it looks like, if I carry this field line out, it looks like the source of my charge is somewhere, say, over here, okay? So looks like I've got a positive charge over here about. So I think my positive charge is going to be about over there. Yeah, so my positive charge will be right there. Okay, so yeah, I think my positive charge is over here, and that's not really a great circle, but it looks like all of the lines are originating from that point over there, okay? So that means oh, are people trying to, yeah, so that means that the amount of flux coming into my room, into my plastic disc here, has to equal the amount of flux going out. So always remember, flux in versus flux out. Remember that example that we did at the beginning? It was like flux of water, okay? So the amount of water coming into your surface equals the amount of water going out. So flux in, if flux in equals flux out, the net flux is 0, unless you have a charge inside, and then it's not 0 anymore. All right, so let's go back here and let's talk about a different case now, where let's say we have, because sometimes we don't always have a spherical shell. Another very well-known example, or at least physicists love to use it. Let's say we have some styrofoam disc or something. And in my styrofoam disc, I have little charges distributed throughout this thing, okay? So I don't know, maybe this is some kind of weird space crystal, but it's just full of, oh, I know what it is. Yeah, this would work. So let's imagine we took a styrofoam ball, okay? And then we take it to the airport or we take it to the doctor and we put it in an x-ray machine, okay? So we put it in an x-ray machine. So our x-rays are coming in here, and x-rays are very, very powerful photons. And so what happens is it starts kicking out electrons. Yeah, this is how we'd actually make it, okay? So we start knocking away these electrons, all right? The electrons are gone. Now, our whole styrofoam ball here is full of positive charges, and they are distributed pretty uniformly throughout this whole thing. Because imagine we just stick it in this big x-ray thing here, okay? And we're using pretty hard x-rays, so we just knock off electrons like crazy. Oh, and fun fact, by the way, they used to have x-rays in shoe stores. So you could go to the shoe store in the early 1900s, stick your foot in there, and they'd put it, and you could see it with x-rays. They had a little phosphorescent screen. You could see an x-ray of your foot. Well, they used really strong x-rays, and so it probably really is very harmful. You do not want to be exposed to x-rays, because if you do, let's say this is some human tissue, okay? Well, you got little DNA molecules in here, these little helixes, okay? Well, all of those genes are held together by electrons. So if in one of your cells, the gene that tells your cells when to stop replicating loses an electron and mutates, then that cell no longer can stop knowing when to divide. And that means that you have cancer, okay? So sad news, guys. Most of the time when you mutate, you don't get cool superpowers. You can't control the weather or read people's minds or turn into a mutant ninja turtle. You just get cancer, okay? So mutations lead to cancer. Very sad. Okay, well, anyways, that's how we get the styrofoam ball that's full of charge, okay? So now we have, so we didn't stick our hand in there, but we have this nice piece of charged styrofoam, okay? Now, we want to know, what is the electric field? Let's start with outside of the ball here. Let's make our first Gaussian surface outside because, well, that's going to be easy. All right, we'll do the easy stuff first. I always like to do easy stuff first. All right, so we're going to do, just like we did with the point charge or anything else, we're going to say that the electric field E here on my Gaussian surface, we'll put it right, we'll put it out here, E times dot dA, okay, is going to equal Q enclosed divided by epsilon naught. All right. Now, I know that my Q enclosed is the total area here. Okay. It's all of the charge in the middle there. Okay. And I don't really need to do anything else because let's call this from the radius here. This is R2. We'll call the surface of our styrofoam ball that's been exposed to X-rays, we'll call that R. Okay. So my electric field is going to be constant anywhere here, and I'm going to say, all right, my electric field is going to equal E times the surface area of a sphere, which I know is 4 pi, and this will be R2 squared. So out here on the surface of my Gaussian sphere will equal Q enclosed divided by epsilon naught. All right, well, we've actually seen this before, and this is just E equals Q enclosed divided by 4 pi times epsilon naught R squared. So this is the same as for a point charge. There's no difference. So if you're outside of a charged sphere, a charged spherical shell, or any charged object, you don't care what the what the shape of the thing is, or how the charge configuration is. You only care about how much charge is enclosed in your Gaussian surface, okay? So if you're outside of this volume charge density, it's just like a point charge, no different, okay? Now, let's go inside here and we'll draw our Gaussian surface somehow in here. So it's smaller than the outside of our ball, okay? It's gonna look like that. So there's our Gaussian sphere. Now we are smaller. We'll call this one, we'll call it R1. Okay, so we want to know, and that would mean if we go inside of here and we're sitting right there, what's our electric field going to be at this point? So, because it might ask you, well, how does the electric field change as you move to the center of the sphere? Right? That might be an important question, and maybe we should plot that later. Yes, I think we will. We're going to plot it later. Okay, we'll make a plot of this, and we will. We'll put it inside of there. All right, we're doing a volume charge density. Okay, so all right, so if we are smaller, all right, okay, we're gonna say, right, we will say that inside of here, we're going to get E. Okay, so we'll start with our integral. The electric field vector dot dA for our surface. So the electric field is constant as usual. It doesn't change on the surface of our Gaussian sphere. And our area is going to give us 4 pi R1 squared. Okay, and this is going to equal the total charge inside. So this will be Q enclosed divided by epsilon naught. All right. So this is only the charge enclosed in my Gaussian surface. That's the only thing that's going to contribute to the electric field. So now you might say, well, okay, that's great. How do I find out how much charge is inside of the sphere? Okay. All right. So now we need to think about this. We need to say, all right, what is the how do I find the percentage of charge inside of my Gaussian sphere? Okay. So, all right, I need to say, all right, Q, this is the amount of charge inside of my Gaussian surface. What percentage is in my Gaussian surface compared to the total charge configuration? So I'm just gonna do a ratio. I'm gonna say the volume inside of R1. Okay, so that's my volume of my Gaussian surface divided by the volume, the total volume. So volume total, right? Times the total charge, right? So I'm just finding a percentage here. Okay, so and then I can add some numbers in here. I'll say the volume inside of R1, that's going to be 4/3 pi R1 cubed. That is the volume of a sphere, 4/3 pi R1 cubed, divided by the volume of the total sphere. So it'll be 4/3 times pi R, the total, the radius of my charge distribution cubed. All right, well, good news, because the 4/3 pi R, that all cancels. Oh, and I need a QT here. So QT is not just a place to get delicious beverages. Okay, so now I have QT times R1 cubed divided by R cubed, right? And that's gonna be my Q enclosed. Okay, so now I'm gonna substitute in my expression right here into this thing. That's what I'm gonna do. So I'm gonna plug all of this right here into my expression and I'm gonna solve for the electric field. Okay, let's go to the next page and I'll write the results. on the next page. So I will have E times 4 pi r1 squared. So E times 4 pi r1 squared will equal QT, the total charge of my sphere, divided by epsilon naught, and I'm just plugging in for Q enclosed, times R1 cubed. Let somebody in to the class. Yes. R1 cubed divided by R cubed. All right. So my R1 squared here is going to cancel right there. That's going to be, those are going to go away. I'm still going to have an R1 here, right? But now I'm going to say my electric field is equal to the total charge divided by epsilon naught. Yes, divided by epsilon naught times R1, because I still have an R1 up here. I'll divide by 4 pi. So this will be 4 pi, and then I've got an R cubed there. So R cubed, remember, was for my styrofoam ball that's been irradiated. Okay. Oh, I know what machine we could put it in. We can put it in the machine that they irradiate bacon with. Have you ever wondered why you go to the grocery store and you see those boxes of bacon sitting there that aren't refrigerated? You ever wonder why that doesn't kill you? Well, it's because some physicist somewhere was like, I'm going to get some nuclear waste, and then I'm going to put some bacon on top of it. And if I do that, then the radiation will kill all of the bacteria. And so it won't go bad anymore. And so irradiated bacon, if you keep it in a plastic bag, will be good forever. It'll never go bad, just like a Twinkie. Okay? So after the apocalypse, just think about this. You can eat Twinkies and irradiated bacon. Yum. Won't that be delicious? Maybe you could have like a bacon wrapped Twinkie. Yum. All right. Anyways, sorry, back to this problem. I don't know why I thought of that. Okay. Okay, so we can write this another way. We'll have QT times R1 divided by 4 pi epsilon naught times R cubed. All right, well, I've almost got a volume here. All right, so what I'm going to do is I'm going to multiply this by 3 divided by 3 in the numerator here. Okay, so I'm gonna do that because I'm just multiplying by 1 down here, and I'm totally free to do that. So I'll have QT times R1 divided by 4/3 pi R cubed times 3 times epsilon naught. Now, why did I do this? Okay, well, oh, now I see what did I do just right there? That became Q2. No, that's QT, the total charge on your sphere. So QT here, okay? Well, I could also write this another way because I can say my volume charge density, that's the charge distributed through my entire volume, is equal to my total charge, QT, divided by my volume, which is 4/3 pi R cubed. Okay, so if I put that in here, now my electric field is just going to equal, what's it going to equal? It'll be equal to rho times R1 divided by 3 epsilon naught. Okay, so that is my electric field inside of my sphere here. Okay, so and what this really means is what this is telling us. Okay, so here's my circle up here. Okay, as I start to make this smaller and smaller, okay, so as R is shrinking, okay, so here's R. As I go into the middle, my electric field is going to get smaller and smaller, okay? And guess what? The only part that matters is what's inside of your Gaussian surface. So anything outside here, so this outer part here, that creates no electric field, okay? The outer part here, that does not give you any electric field in the middle. The only part that gives you an electric field is what is inside of your Gaussian surface right here. Okay? The outer part, it doesn't matter. Only the inner part. Okay? So if we look at this part here, okay, as R1 gets smaller and smaller, then right here, then our electric field is going to go to 0. And if R1, when we get to the middle, so we're right here in the middle of this this volume charge, that means our electric field is 0. So right here in the center, our electric field is equal to 0. Okay, well, this is about everything. We've done a lot with Gauss's law. Now we did lots of different shapes. I want to look at a problem now, and then next time we're gonna go on to another chapter. We've pretty much done this one. Let's take a look at a problem really quick. Oh, and Wiley has booted me out. That's okay. I'm gonna log back into Wiley here real quick, and I'm gonna bring up a problem, and we'll take a look at it because the homework is due today. If you have a situation in your life, you can turn in later, but please let me know what's going on. I'm pretty understanding. So if you have something going on, if you have to go to the doctor or you're traveling somewhere, hopefully you're not traveling anywhere, but just let me know. And I know things are in our universe are strange right now. So I'm happy to help, but just let me know what's going on. Okay. All right. Oh yes. Let me share my screen with you, and we will quickly go through a problem. All right. I have to get back to Zoom. Click share screen. And if you need to go to another class, you can leave, but I want to talk about this problem. Okay, so here we go. Problem number 14. All right, this is flux in a non-conducting shells. Right, so charged particle is suspended at the center of two concentric spherical shells. They're very thin and made of non-conducting material. Figure A shows a cross section. Okay, figure B gives the net flux through the Gaussian sphere centered on the particle as a function of the radius of the sphere. Now, what's important about this problem compared to the one where you have a metal conductor? In this problem, there are no regions where the electric field is ever 0. Inside of a metal shell, you would have a region where the flux is 0. Okay, so as we start out here on the left, that is where R equals 0. That's where R equals 0 right there. And then right here, that is the radius of our first shell. Okay, so that's the radius of shell A. So for part A, it says, what is the charge in the central particle? All right. Well, we know what the flux is. It gave it to us right here. Okay, so then you can of course use the equation for flux right here. All right, so flux equals Q enclosed in the surface there. Q, I can't draw a little e right now. Okay, that's Q enclosed times epsilon naught. Oh wow, that's a terrible epsilon. All right. So that's for the inner region. We find the flux on the inside there, okay? And so we know what that part is. All right, so let me switch to my document cam. All right, so let me draw out this picture real quick. Okay, so in the inside region, in my sphere here, I know what the value is. All right, so this is Q. This is going to be Q enclosed here. That's going to be my central point, okay? And so I'm going to calculate the flux. I'm going to get the flux in there. And my plot looks something like, here's 0. And then it's going to look like this. And it will go, what's it look like? Oh, and it will go back up here, okay? So when I look at this plot, what that means then is that each one of these shells, so this shell here, okay, and this other shell over here, okay, they each have some charge in there. So for my second Gaussian surface, I'm going to go out here, and I'm going to say, okay, my total flux is going to equal, so this is for part B now, okay? My total flux is going to equal, it'll equal the Q total over epsilon naught, right? And Q total is going to equal the Q of my point particle plus Q of shell A. Q of shell A. And this is all divided by epsilon naught. So now I can figure out, using algebra, what the charge here is on shell A. Okay, and I do the same thing for part C. Okay, and I use my plot here, and now I can find the charge on each of those shells. Okay, well, that's it for right now. Now I'm going to go back, and I'm going to do the experiment again where I make the tissue fountain. So if you'd like to see me playing with electricity, again, you're welcome to stick around, and we can talk about it. Or if you need to go, please go. I will see you guys on Wednesday, and we're going to be moving on to chapter 24. Thanks for coming. I'll see you guys later. All right. There we go. So we're back here. I'm going to get my experiment going again. Alrighty. So again, we have our plastic bowl here, and we have our metal conductor. And our metal conductor here with this clip, the clip goes to my lamp, and so it is grounded. And so I'm making a metal shield here, because if this is grounded, it's a Faraday cage, and it's going to block all of the electric field. And so what I'm going to do is I'm going to show you the difference between these two. So I'm going to take a piece of tissue here, and I'm going to tear up my tissue. I'm going to put it in my plastic bowl here. Yes. I'm going to tear up this entire piece of tissue, and it's going to make a huge mess. Okay, and I'm going to put this on top of my Van de Graaff generator, and so there's going to be a huge electric field, and it's going to be really awesome. And I didn't record it before. All right, so I guess you guys want to see it again? Let's do more tissue this time. Let's make it even better. I'm gonna get my vacuum up later. I'll have to clean all this stuff up, but it's pretty awesome. All right. So I guess, well, you can't really do it at home because you don't have a Van de Graaff generator, but that's okay. All right, so wow, this is gonna be a huge mess. This is even more tissue. All right, here we go. We're gonna put it inside here, because the main point of this is that this plastic bowl will not block the electric field. Electric fields go right through an insulator, okay? It might keep you from current moving, but the electric fields will penetrate through this. And it can keep current from flowing, but it will not protect you from the electric field. All right, so here we go. I filled this full of tissue. I'm going to turn on my Van de Graaff generator, and now we're going to see it. I'm actually going to use this as a shield here. All right, actually what I'll do, first I'll put it into this metal container here. All right, so this is my metal grounded container. There we go. This is my metal container. And what's great about this is I'm going to turn on my Van de Graaff generator, and literally nothing is happening to here. Okay, I can feel the electric field on my arms, but nothing happens to the tissue. And I can discharge this thing, and there's a lot of charge on this. Okay, you can see it. Whoa! Oh, that scared me. I didn't feel anything. That scared me. So there was an arc between this. So if I'm touching this, I can put it on here and nothing happens, because this is grounded. It's hooked into the Earth's ground. The Earth has an infinite amount of charge, basically, because of all of the water and salt. So there's a lot of ions in the soil. But now, I'm going to put my tissue into this plastic bowl. Okay, here we go. I'm just gonna set it on there, and I'm gonna stand back. I'm gonna hold the metal shield here. Oh, see, it came ungrounded. That's bad. All right, my metal shield is grounded. I'm gonna turn on my Van de Graaff generator. Let's get a little better view. There we go. Yes. There we go. Turn this thing on. Oh, there we go. Ah. Oh yeah. See. Oh my gosh. Well, kind of fell off, but you can see it. All right, let's do it again. I'll get some tissue in here, and hopefully this won't fall off. Yeah. Try it one more time because it kind of fell off there. All right. We got all our tissue in here. We'll try it again. There we go. Hold this up here. Ah! Oh, it doesn't want to. All right. Well, anyways, that's enough for today. So thanks for coming to physics class. Oh, there's a little charge there. All right. Oh yes, and one other thing, I can shield myself here. See, I can put my head in this. Oh, and nothing happens. Oh, see. But if I do the plastic on my, I'm just gonna do it. I won't do it a lot because I don't want to shock. Let's see if I can feel the electric field here. Oh yeah. I can definitely feel it going through the plate. My hair is sticking up on my arm here. Oh yeah, I can feel it. It's not as strong as if I go right there. Oh, maybe let's charge up here. There we go. All right. Oh yeah, I can feel it through there. All right, guys. So this does not block electric fields. This does. Metal will block it. Plastic does not. All right, thank you. Have a good day, and I will see you guys next time. Thanks for coming, guys.
Thank you.
Thanks.
Dr. Osby, I had a quick question. If those materials were wet, would the outcome be any different?
Ooh, well, I think if they were wet, they would stick to the sides. So I don't think they would fly out as much. But, you know, water is a polar molecule. So actually, next time I'm going to make a video of this and post it. But water actually is affected by the electric field. There's some really, really cool properties of just normal liquid water. So if you have an electric field, if you have something that's strongly polarized like this, and you pour water down, it will actually bend due to an electric field because water is a very polar molecule. So it's got a very strongly positive and negative side, and so it definitely will be affected by an electric field. So but I'll post a video about that because I don't have all the stuff for that. But yes, water is affected by an electric field. So now as for these little tissue papers, yeah, I don't know if they would fly out because they might stick to the wall. So I don't know. I don't think it would really change it that much. Water, you know, well, no, that's an interesting question because if water is, you know, water is conductive. So like if you get water out of your tap water, it has a lot of ions in it. And so if you had this conductive material, even if it was water, the water could act as, I think it would act as a Faraday cage. Okay. So that means if you were on the surface of the water, okay, and say lightning hit it, you would get electrocuted. But if you were underneath it, down below in the water, you might be safe because the surface of the water is very conductive. And actually, I think current can move through the inside of the water, but mostly it travels along the surface. So I think water could act as a Faraday cage, but you'd want to have it like in front of you, basically. So yeah.
I was just wondering. Thank you so much. I appreciate that.
No problem. All right. Talk to you later.
Talk to you soon, Wednesday, Dr. Osby.
All right. See you later.
Thank you. Like and subscribe down below.